Good day, everyone. Today, we are going to discuss an important topic in organic chemistry that forms the basis for understanding many pharmaceutical and biological processes. The topic includes polarity of bonds, polarity of molecules, intermolecular forces, melting point, boiling point, solubility, ionic and non ionic solutes, protic and aprotic solvents, and ion pairs. All these concepts are interconnected, so try to understand them as a continuous flow rather than separate ideas. Let us begin with the polarity of bonds. When two atoms form a chemical bond, they share electrons. However, this sharing is not always equal. The extent to which an atom attracts electrons is known as electronegativity. If two atoms have the same or very similar electronegativity, the electrons are shared equally and the bond is called nonpolar. But when there is a difference in electronegativity, one atom pulls the electrons more strongly than the other. This creates a partial negative charge on the more electronegative atom and a partial positive charge on the other. This unequal distribution of charge makes the bond polar. The greater the difference in electronegativity, the more polar the bond becomes. Now, moving from the individual bonds to the entire molecule, we come to the polarity of molecules. A molecule may contain polar bonds, but that does not necessarily mean that the molecule itself is polar. The overall polarity depends on both the polarity of the individual bonds and the shape or geometry of the molecule. If the molecule is symmetrical, the dipole moments cancel each other and the molecule becomes nonpolar. On the other hand, if the molecule is asymmetrical, the dipoles do not cancel and result in a polar molecule. So, both bond polarity and molecular structure must be considered together. Next, let us understand the intermolecular forces. These are the forces of attraction between the molecules and they play a very important role in determining the physical properties. The weakest of these are London dispersion forces, which are present in all molecules, especially in non-polar ones. Then we have dipole-dipole interactions, which occur between the polar molecules. The strongest among these common forces is hydrogen bonding, which occurs when hydrogen is bonded to highly electronegative atoms like oxygen or nitrogen. The strength of these intermolecular forces directly affects how molecules behave in different states of matter. Now, based on these intermolecular forces, we can understand the melting point. Melting point is the temperature at which a solid changes into a liquid, and if the intermolecular forces holding the molecules together in the solid state are strong, more energy is required to break them and the melting point will be high. If the forces are weak, the melting point will be low. Other factors such as molecular size and shape also play a role. Larger molecules generally have high melting points and more symmetrical molecules pack better in the solid state, which also increases the melting point. Impurities tend to disrupt the orderly arrangement of molecules and therefore lower the melting point. Similarly, boiling point is the temperature at which a liquid changes into vapor. Again, intermolecular forces play a key role. Stronger forces require more energy to separate molecules into the gaseous phase, leading to higher boiling point. Molecules capable of hydrogen bonding usually have significantly higher boiling points. Molecular weight also affects boiling point, with heavier molecules generally boiling at higher temperatures. Additionally, straight chain molecules tend to have higher boiling points compared to branched ones because they have larger surface area for intermolecular interactions. Now, let us move to solubility. Solubility is the ability of the substance to dissolve in a solvent. A very important principle here is that like dissolves like. This means polar substances tend to dissolve in polar solvents and non-polar substances dissolve in non-polar solvents. This happens because similar types of intermolecular forces can interact effectively. For example, water, which is a polar solvent, dissolves in salts and sugars, while non-polar substances dissolve better in organic solvents. Solubility depends on factors such as polarity, intermolecular forces, temperature, and the nature of both solute and solvent. At this point, we should differentiate between non-ionic and ionic solutes. Non-ionic solutes are substances that do not dissociate into ions when dissolved. They remain as whole molecules in solution and usually dissolve through hydrogen bonding or dipole interactions. These solutions do not conduct electricity. On the other hand, ionic solutes dissociate into positively and negatively charged ions when dissolved, especially in polar solvents like water. These ions interact with the solvent molecules through ion dipole interactions, and as such solutions can conduct electricity, which is why they are called electrolytes. Now let us discuss protic and aprotic solvents. Protic solvents are those that have hydrogen atoms attached to the highly electronegative atoms like oxygen or nitrogen. Because of this, they can donate hydrogen ions and form hydrogen bonds. This makes them very effective at stabilizing ions in solution. Common examples include water and alcohols. Aprotic solvents, in contrast, do not have hydrogen atoms capable of hydrogen bonding. They cannot donate protons, although they may still be polar. These solvents are useful in certain chemical reactions where proton donation would interfere with the mechanism. Finally, let us understand ion pairs. When ionic compounds dissolve, we often assume that the ions completely separate. However, in some cases, especially in solvents with lower polarity, the oppositely charged ions remain associated with each other to some extent. These are called ion pairs. In some cases, the ions are in direct contact, forming contact ion pairs. In other cases, solvent molecules come in between them, forming solvent-separated ion pairs. The formation of ion pairs depends on factors such as nature of the solvent, its dielectric constant, and temperature. In solvents with low dielectric constants, ion pairing is more likely because the solvent cannot effectively separate the charges. So, when you look at all these concepts together, you can see that they are closely related. Polarity influences intermolecular forces, which in turn determines melting point, boiling point, and solubility. The nature of the solute and solvent, whether ionic or non-ionic, protic or aprotic, further affects how substances behave in solution. Understanding these relationships is essential for predicting how drugs and chemicals will behave in biological systems. Thank you.